Rafferty? No.
Somebody take over the team and ask
Armand.
Reagan, like the
Ooh,
president?
Ricardo. Ask his brother. Is it Ricardo? There's no way.
Oh yeah. He wouldn't tell me.
All right, Sam, can you kill the lights, please?
I'll find you.
That's fine. I'm sure that somebody will eventually come up with it, but I am pretty confident it won't be within the next hour. I don't care how you come up with it, as long as it doesn't involve like stalking.
Did you have Edgar? Did you call? Oh, true. Is it spelled weirdly, or it's just not a common?
It is not a common name in.
Russell?
Alright, I just remembered I need to have this thing up.
Raleigh.
Cross sections.
What if it's like the normal name, but it's spelled weird name? What if I email your brother right now? Tell for 7 letter names.
He's gonna want to know why are we talking about that and not calculus. Alright, steps to find solids using known cross sections. So yesterday we talked about like the general idea, and then here's kind of more of a step-by-step process. So while you guys write that down, I'm going to get up the first example here on the board.
That's your ID card. Oh, what? Maybe. You never know.
It's from there? It's fun?
No.
No.
He has plans or something.
Oh.
Yeah. That would be very distracting, so please stop.
Oh, triangle. I read that as delta S.
Oh yeah, sorry. Triangles, obviously.
That doesn't. I read that delta. I delta S.
So when we are going to find a volume of a solid generated by known cross sections growing out of the graph, the first thing you want to do is sketch the graph. So step one is, all right, let's look at the graph of these curves that are specified to us and see what is the enclosed space in the plane. Then you want to know, okay, which axis are these cross sections going to be perpendicular to? So are our cross sections, whatever they are, going to be perpendicular to the x-axis or the y-axis? I would recommend that you sketch a little rectangle on the graph showing that cross section. Then over on the side, you'll draw a 2D cross section picture. So if you're dealing with triangles, over on the side, you'll draw a triangle. and that'll be then kind of where you use to find the area of the cross section. You'll want to put the base, like the bottom side of that cross section, should kind of correspond to the the rectangle that you drew in the graph that was perpendicular to the specified axis. Now, a lot of these steps aren't going to make a whole lot of sense until you see them in action. So if you're like, what in the world is he talking about? Fair enough. Once you've gotten that, you're going to find the area in terms of the base, and then you'll have to replace the base with stuff in terms of x or y. And then you set up your area formula and set up your volume integral. So there's a lot going on here. So once you guys have those down, I'll kind of walk through the steps one at a time in the context of this example 6 over here on the board. But I want you guys to have all the notes down first, especially those of you online, because I'm going to need to move the camera away from there over here in order to be able to show you this thing over here. Yes, ma'am. Sure. What did I spell wrong? What step are we looking at? Step 4. Right. All the way. The base of the cross section is the side that lies in the plane of the graph. Yes. So yeah. Delete that down. Yes. And I'll need to remember to later on go back in and fix that. No, because yeah, sure, why not? But I thought that was going to happen, so I can't edit stuff while it's frozen. Stay there. Good. So that I could do other stuff on my laptop without just getting messed up. Okay. My favorite candy? No, gross. I like Reese's okay, but like I prefer the Trader Joe's versions of the Reese's cups to actual Reese's.
What?
I do like Twix. Twix are good. I like Kit Kats. Snickers are all right. I prefer Kit Kats and Twixes.
You're disgusting. Is it really?
They're all right. I like Tootsie Rolls.
No, don't say that.
They're better than Skittles.
I wouldn't choose.
I mean, everything's better than Skittles.
That's not true.
You don't eat
What about Mike?
I don't eat Mike and I.
Ooh, Mike and I.
My favorite thing about Mike and Ike's is that they got Lower Merion in the news. So years ago, so over in Lower Merion, they would get I think you could like borrow a school laptop, and they had Macs. So some kid over there borrowed a school laptop, took it home, and then forgot to return it when he was supposed to, or planned on stealing it. I don't know, but he didn't give it back to the school in the time that he was supposed to. So some genius assistant principal over there, they had this function that an administrator could turn on the camera remotely. So he turned on the camera of this particular laptop to, I guess, try to find out where it was. I don't know what seeing the surroundings would do for him, but he turned on the camera remotely and saw this kid in his bedroom eating Mike and Ike's and thought he was seeing this kid pop pills. And then had the genius idea of the next day in school, call the kid down to his office and say, "What were you doing?" And the kid said, "What were you doing?" Peeking into my bedroom through that laptop camera. I think we got a bigger issue here than... Also, those are Mike and Ike's, not pills. So this got into the Philly Inquirer, and it was like front page news for weeks. It's like, yes, it's finally some other school that usually is able to sweep things under the rug so it doesn't get in the news. So that's why I like Mike and Ike's. But as a candy, they suck.
What? Do you know our Chromebooks in the future?
I don't know,
It probably does. I guarantee.
but I wouldn't be surprised if it does.
Well, this always
I would-
seems to
I'm very skeptical of all technology that has like recording capabilities.
Yeah.
Which is why in my house there is no Amazon Echo or whatever the other things are. But even your cell phone is recording you.
Yeah.
There was an article about the Echo. It was listening in like a family.
Yeah.
Do you have?
I mean.
Yeah,
no,
but
I
it's
mean,
listening.
like,
Yeah, I mean,
someone
how does it
was
know
listening.
to start listening then? It's got to be listening for that, which means it's listening for other stuff. It's listening to everything. It's taking all that data that they hear, sending it off to the cloud, selling that data to advertisers to try to advertise to you more effectively.
They still know, like they can hear what, like it records what you say and sends it back to Amazon, and Amazon sells that information. You can just change your location. So just change the fact that they know what you say.
And it's not just Amazon. I'm sure like Microsoft does the same thing with theirs Cortana. Apple does the same thing with Siri, I bet. So
I wonder even if you turn Siri off, that goes off.
probably,
In the background.
I bet it does.
So
I bet
all
most of these, I'm sure most of these to actually turn something off is a lot more work or a hammer.
Well, my mom bought like a smartphone camera for my dog when we went on vacation.
Mhm.
She just had a sitter, and like it's usually off. And even if it's like off and it's like not like lit up, like, it'll still record us. It's so bad because it's on the same system as like my fridge, my Samsung. Sometimes you can watch the camera from my fridge that has on it. So you can like see me actively in my living room.
Like you know the smart fridges.
Yeah, I'm trying to like keep my house as dumb as possible. I don't want a smart fridge. I don't want a smart thermostat. I didn't even want the smart phone, but it became more expensive not to get one than to keep my.
Wait, when did you get a phone?
I had like a flip phone for years. I only got the smartphone like 5 years ago. Why? Because I know myself, and I know that if I got the smartphone, I will become an addict. Yep. So
What do you do?
mostly like read articles. I used to just scroll on Facebook, and I was like, "This is stupid," so I killed Facebook. Yep, I killed it. If Facebook as a company could be burned to the ground, that would be so good for the world. Anyway, Meta, whatever it is, that too. Meta, like, what's even the point? Like, you see the real world? That's not good enough for you? Go into really lonely land and. So, back to math. Sorry, people at home. Yeah, they seem to be fine. So volume of the solid generating by having equilateral cross sections, equilateral triangle cross sections, thank you, come out of the graph at you from the region bounded by these three curves. So first thing you should do is, all right, curve, 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 graph it. So I'm going to come over here, hello here, and I'm going to make a graph. And I've got f of x equals 1, y-intercept, minus a half x, so the slope is negative 1/2. So down 1 and over 2, that's f of x. G of x equals negative 1, y-intercept, plus a half x, so up 1 over 2, that's this line, there's g of x. And then x equals 0, that's your y-axis. So this is our region that's going to be enclosed. Next, instead of doing what we've done up to this point of take that thing and spin that triangle around some axis like y equals 2, what we're now going to do is say, let's play imagine. Imagine cross-sectional triangles growing out of the page at you. And these are going to be equilateral triangles. So what I'm going to do here is I'm going to draw the base of that triangle that lies in the plane on the graph, and the base of these triangles are going to be perpendicular to the x-axis. So this is what I'll call my representative rectangle. The width of that is like dx, and that's the base of my triangle. So that's one of the three sides of your equilateral triangle. That's step 2. So step 1, draw the 3 curves on your graph. Step 2, draw your cross section and say, oh, we're perpendicular to the x-axis, so I'm going to draw this rectangle perpendicular to the x-axis. And then step 3, draw your 2-dimensional cross section. Our 2-dimensional cross section are equilateral triangles. So over here, I'm going to draw an equilateral triangle. Because it's equilateral, ding, ding, ding. Why? Okay, so I can have a picture. So this is not this shape. This is the cross sections coming out of the page. So this is the base of some triangle. So this base corresponds to the bottom side of my cross section. So this is my 2D cross section. And imagine this shape is oriented so this side is this thing and it's coming out of the page at you, so you have like a triangle coming out and you could like impale your eyeball on the corner that's out of the page.
The eyeball.
Yeah, you just come up here and like stab your eyeball in. Boom. So if soccer balls were like pointy, that's what you have to worry about when you get a ball, right? So bad analogy again. So you have your 2D cross section. Then you say, all right, I need to know the formula for the area of this thing in terms of B. So area of a equilateral triangle. That's not a very good equilateral triangle, so I'm just going to call it A. So the area, and what was the formula for the area of a equilateral triangle yesterday? Was it 3/4 B squared? I'm so good at remembering things when you say them to me. All right, thank you. So you're going to want to learn these because you don't want to have to go back and rederive that area every time. Now, let's suppose you don't memorize it and you do have to rederive this area formula. How would you do that? Well, let's come over here and see if we can do that on the fly. So what if you've forgotten your area formula for an equilateral triangle? Oh, no. So we know that triangle areas are 1/2 base times height, right? So if we draw the height here, boom, we'll call this H. These are both B. And now what's this thing right here? B over 2. And what we need to do is find out H in terms of B. How would we do that? Solve for H using what magic theorem? The Pythagorean theorem. Hooray for the dead Greek guys. So we have B squared plus B over 2 all squared. That's a lie. H squared plus B over 2 all squared equals the hypotenuse squared, right? So the hypotenuse of this triangle now is B, and the legs of this right triangle are H and 1/2 B. So you do your Pythagorean theorem. You have H squared plus B squared over 4 equals B squared. You solve for H squared, and so when you subtract over 1/4 B squared, you get 3/4 B squared. And then you take the square root to get H. And H is √3B over 2. Ta-da! See? Simple, right? Then that's H, not your area. So you got to take this, put it here, and say your area for this thing is 1/2. Okay, good. This is a good reaction. I want this to be a reaction. I want this to be big and ugly and scary. so that you look at that formula and says, I'll just memorize it. So 1/4 times base times height is √3 over 2b. And when you do that, you have √3 over 4b squared. And it turns out, looks like that was wrong.
No, that's what you have on the
Yeah,
formula. That's what it's on the formula.
Oops! So it's a good thing we did this. Go back to yesterday's notes and fix this thing, because it turns out I lied to
So
you.
basically, your
Whoa.
whole point of doing Pythagorean theorem with that was actually incorrect.
It is good to do it, but hopefully only once.
So when we got the wrong answer, but now we have to do it because we can't trust you.
Well, now you know. So let me look at.
Let's do all of them then.
I had it written down yesterday in my notes. Look, how could I possibly have messed this up getting it on the board? Right? It's like an absolute mess. How could I? Because it's impossible to read. So, oops.
Oh, but when
erase
I
all
have bad red hair, it's
Oops.
a problem.
You should erase all of it and then rewrite
So where is it? Oh, there it is. Oh yeah, I even got a circle. I don't know how I messed this up. Actually, it's pretty clear now. Whoopsies. So, whoopsies.
I think we should have done that whole entire problem without the root. How does this apply to the real world?
it. Oh yeah.
Don't worry about that. I haven't talked this down.
I was
One thing at a time. One thing at a time. Are you sure you want me to answer that question?
Yes.
So that question gets pretty ugly when it does get answered. So,
Okay, do it.
so the area formula for an equilateral triangle, in terms of the base of the triangle, is that thing.
Right.
And if you don't memorize it, or if you mess that up, your memorization of it, then you're stuck with going back to like creating an equilateral triangle and re-deriving the area formula for it, which you probably don't want to do every time. So it's worth seeing the derivation one time and then saying, I don't want to do that derivation every single time I have cross sections that are equilateral triangles, so it's worth it to me to just learn that thing. And sorry for lying to you yesterday. I apologize.
We deserve
An apology board point.
Because
Honestly,
Actually,
Maybe apology cookies will be better.
Oh,
So go
I
ahead.
like those. You can make some without chocolate. It doesn't really
Can you bring it up?
I am a one-trick pony. I only do chocolate chip cookies. I'm sorry.
Well, then make it, but just don't put chocolate.
Can you do that, please?
What?
I can put in fewer chocolate chips than normal,
No, don't
and then
do
try
that.
to
I'll
make a
make
few
your
cookies that are neutered and have no chips in them, and then you can have
I'll make
dibs
your
on
naked
those.
You just not like chocolate chips.
I do not like chocolate. What?
Or I could do some with raisins.
No.
I'm kidding. That's terrible. All right. So anyway, back to here. So you have your area for the cross-sectional triangles in terms of B. At this point, most of your heavy lifting is done. What you now need to do is replace B with some expression involving X. You're going to come back over to here and say, well, what is this distance from the top to the bottom? So now we got to come over here and say, well, what is B in terms of X? How far is it from the top curve to the bottom curve? And that's going to be f of x minus g of x, because the top curve is always f of x, and the bottom curve is always g of x in this scenario. So when you do that, f of x minus g of x is 1 minus a half x. That's not how you do 1 minus. 1 minus a half x. And you're subtracting g of x, negative 1 plus a half x. And you get b equals, oh yeah, you're right, 2, so 2 minus x. Yeah, duh, of course this is 2 times that, yes. So you get 2 minus x, that's b. And then you take that for b, and you shove it up over in here in your area formula, and you get your area formula in terms of x rather than b. And now you're ready to go to your volume formula, which I haven't shown you yet, but I will soon.
Is it gonna be correct?
You should double
That's a fair question.
You should double check.
I just want to know what kind of dress they were on. Why is it?
Yeah, what is the application?
How does
All right, so back to here. We'll answer that. we'll answer that later. Back to your notes. So we've gotten to the part where we say, hey, here's the area formula for a single cross-sectional triangle. Now what do I do with it? An integral. What's the integral? Ta-da! So your volume formula is the integral from A to B along the x-axis, if you're doing stuff in terms of x, of the area formula dx. So once you have your area formula, you just shove that into an integral, and you're good. And you just make sure, oh, we're going along the x-axis because we're in terms of x, so that would be from 0 to 2. If we were going along the y-axis, you'd go along the y-axis and you'd be doing stuff in terms of y. And you can see these nice pretty pictures here. You can also find these pictures on, I forget what page, 463. You will always be told the cross-sections. You have to be told the cross-sections. So in this case, the cross-sections are squares. You can maybe see that here. I'll try to make it a little more. Oh, yeah. I don't know what happens if they're unknown cross-sections. Let's assume that never happens. Or is that a BC thing? I don't even think that's a BC thing. Yeah, that's a fair question to say, well, I mean, the known crosses are unknown cross-sections. It's like, if I tell my kid about World War II, and they're like, well, if there's World War II, there must be World War I. So that's a fair question. I don't think there's a situation where we're going to do unknown. Well, I know there's not a situation where we'll have unknown cross-sections. We will always know the shape of these cross-sections. Whether that's a thing at all, I don't know. It's not something that I've ever remembered running across in my years doing math in college. I think that's trying to be a square, but it's not clear. This is why I would say maybe look at the textbook. The picture in the book. It's trying to make it like semi-three-dimensional. Picture frame. Yeah. It's trying to be a rectangle or maybe a square. If you want to see a better picture of it, go to page 463 in the textbook and you can do that.
Alright, so people actually do this in the real world. How do they know what the cross-section is?
Usually I would imagine it has to do with like they're building something. And
Oh, so it's
if they're building something, they know what they want to build. They've designed it.
like building would be.
Yeah. So it's like we have some sort of base and maybe you're like wanting to build a bullet or something and then so there's cross sections or something. So there's your formula. So we come back over here. Nope. You come back over here. Thank you, Sam. And you're going to say, all right, volume equals the integral, no pi involved because we're not rotating this about some axis, so it's not like circular in any way. So just the integral of the area. So the area is root 3/4 times 2 minus x all squared dx. So just take this area that you found, dump it in an integral, and then you got to figure out your bounds of integration. And because we're doing this in terms of x, we want to look along the x-axis. And I forgot to label this out here, but that was 2. So we're going from 0 to 2 along the x-axis. And now we're on our way. So it seems really complicated when you first run into this. And also when you second run into this and third run into this. But once you get to this idea of, okay, I need to figure out the area of this two-dimensional shape in terms of the base, where the base is the side that's lying in the graph. If you can get the area, that's the hard part. Because once you have the area in terms of x, you just plug that into the integral, and you're good to go. Arif?
Where's the pi?
So yeah, so there is no pi, because we're not doing a rotation. So you got the pi with the washes and disks, because we were taking this thing and then rotating it about some axis, and as soon as you're doing a rotation, you're kind of generating circles. And so like pi r squared is the area for a circle. Here, you're not rotating anything. You're getting a whole bunch of triangles. That's the area of all the triangles. And then you're integrating across. and basically adding up all those triangle areas to get the volume. Sam?
So is the shape of the actual like lines being triangles?
Yes, that is purely
It has
coincidental.
nothing to do with like.
This could be sine of x up here and negative x squared, and then you would have b equal sine x minus negative x squared,
And they still all be
and it would still be two-dimensional triangles that are growing out of the page at you. Noel? Yes.
Second question. So with the rotation thing, were we rotating it because we were told to rotate it, or were we rotating it for a specific reason?
We were rotating it because we were told we're going to take this thing and rotate it about some axis.
So this thing is like already 3D.
Yeah.
The other thing is
Mm-hmm. This thing is like, it's two-dimensional, and then we make it 3D by imagining these cross sections come out of the page. The other thing is two-dimensional, and then that we make 3D by rotating it about some axis. So in both cases, we're starting with a two-dimensional figure in the plane, the XY plane, and then we're making it three-dimensional in some way or other, either by rotating it, or in this case, by imagining cross sections of some shape come out of the page. Will we be, yeah, as long as this is a constant multiplier, you can absolutely pull that out of the integral when you go to do it. So at this point, we're done with the notes, so I can turn that off. So we could go to that integral and say, all right, well, let's go ahead and evaluate this integral and find out, well, what is that volume? Sorry. So if we take that integral over here, where we'll have some space to do the work, the root 3/4 can come out because it's just a constant multiplier. So that just clutters up the integral. Maybe go ahead into 2 minus x squared and multiply that out, and you get 4 minus 4x plus x squared, right? And then you can integrate this. They have root 3/4 just chilling out front, times 4 becomes 4x becomes minus 2x squared, and x to the second becomes 1/3 x cubed, and this is going from 0 to 2. This in here is a polynomial. We love that the lower bound is 0, so we really only need to worry about the 2. And so we have root 3/4 times 8 minus 8 plus 8/3, yeah. So those cancel. We have root 3/4 times 8/3. That's going to be what? 2 root 3 over 3. Or 2 over root 3. Whatever makes you happy. Oh, like take this 4 and distribute it through and have 1x or 1 minus x plus a 4th x squared, and then just a root 3 out front. That would work too. I don't know if there's any advantage to doing that or not. I do think what your first suggestion was of getting the root 3/4 outside before you integrate is definitely an advantage, because they don't have that messy constant floating around. Thank you. So there's cross sections. You're all set, right? Okay. Let's look at, let's see, this says example 7, and then I crossed it off and said nope. So I guess we're not doing example 7. So I think we'll now go to the examples packet. So this packet is going to be your homework for, I forget what night. It said due Thursday. Ugh. Friday. It's due Friday. So I'm going to go back in here and change it to be doing Friday, because we're only just now starting to look at this. So you have your, we're going to have 2 of these things for cross sections. We're going to work on it today in class and tomorrow in class, just working through the examples. And then whatever we don't get to will be homework due on Friday. and then we'll start the second packet on Friday, and we'll get through whatever we get through in class, and then I'll decide if that's due on Monday or Tuesday.
Wait, the homework packet or the long stuff?
Wait, is there homework? Is there homework in the textbook or?
You said that one.
Oh, right. There's textbook homework that was assigned last night.
Yeah, that was the.
That's due tomorrow.
Yeah.
Okay, yeah. Okay. Rewind.
Oh.
So,
and then this problem
The
is
textbook homework that I assigned last night is due tomorrow. This packet will become homework tomorrow night and will be due Friday. In class today and tomorrow, we'll be working through these examples. Whatever we don't finish from these examples will become homework that I collect on Friday. And then you'll get a second packet on Friday, and we'll do the same thing with that. So between these two packets, we will have lots and lots of chances to work on practicing cross-section volumes. And I just looked at this more closely, and that says packet number 2. I'm going to go back there and get packet number 1 real quick. Yeah, Dave, you're on very well.
Oh, that's her.
Here you go. Here you go. Pass one up to Renee.
Yeah. So I made it bigger this time. Maybe this time.
We should have correct.
If
Like,
you
I
have
have cameras in my room.
so maybe, or you could like just pop it. Really just
Good idea.
I'm going to take that.
if you think about it, it's less work than having to rewrite it.
That's
It's
true.
not like one
Especially if I have to rewrite it like
and then, reach the
4 or
word
5
for it.
times. Did everybody get one?
Not the, that's what we used to do, right?
No, we did Albert's. But they're
No,
not
you have to-
Albert ready yet.
Wow. And
Oh,
at
really?
They're coming along. I mean, look at the class average of the last quiz.
Literally. Well, no. That's been us.
Kayla needs to ask something.
Yes, ma'am.
For a question like this, why do we have to do all this work? Why can't we just treat it like a pyramid with that's what we make. And just do that all.
We're not making a pyramid.
But you said they're all coming out like this.
They're all coming out. So there's going to be like a ridge here.
It's not a, there's not a central.
So there's not like it's not all coming up to a single point. It's coming up to a sharp edge. I guess the point is down here. This is the point. Because as we go along, this base gets smaller and smaller and smaller. So like the cross-sectional triangle here is extremely tiny, but the cross-sectional triangle up here is really big. So if it's coming to a point, it's coming to a point right there. But most of the time, and then I guess the base of the pyramid would be back here.
It's like, think about how you stack stuff.
Oh, okay, so it's going down.
Yeah.
Okay. It's not something.
Thank you, Noel.
Just take a picture of that.
All right, so first example here, we'll call it 1A. There you go. Region B is bounded by the x-axis, the vertical line x equals 9, and root x. So we start with making a graph. So. I just drew it, and then I start filling in tick marks. If it's too long, I erase some. If it's too short, it wasn't that remarkable. So we have x equals 9. We've got x equals 0. And then, the x-axis, sorry. Not x equals 0, x-axis. And then we've got the line y equals root x. So plot a few points from there. And boom. So that's your graph. Any questions so far? Then we say, how are the cross sections going to be oriented? And we're going to say the cross sections are oriented so that they're perpendicular to the x-axis. So I come into the graph and I draw the base of one of these cross sections here in the graph so that it's perpendicular to the x-axis. And then we need to know, well, what's the shape of that thing? Oh, it's a square. So this right here is the distance b. We'll always call that b from the top to the bottom of the area. So that base of the cross section is length b. And then we come over here, and what do we draw off in the margin? Draw a square. And squares are nice. And the bottom edge of the square is b. And then we say, well, what's the area formula for a square in terms of b? Not s squared, it's b squared. Because everything's going to be in terms of b. Then we go back over to our graph and say, we need to get b in terms of x. So what is b? How far is that from the top to the bottom? Root x minus 0. So top minus bottom is root x up top and 0 on the bottom. So root x minus 0, which we'll normally call just root x. So you get your distance across the region from the top to the bottom, that's b. And we take it and we put it into our area formula. So our area formula now in terms of x is what? X. All right, the first one was fairly heavy, especially for the first one. This is about as easy as they're ever going to be. Because you get, in the end, you're dealing with the easiest shape you can. Squares are better than anything else. And then the way our region is set up, our base b turns out to be just exponents in terms of x, so our area is a equals x. Now, what do I do with that? Volume equals 0 to 9, because we're going in terms of x across the x-axis. X dx. So not even x squared. The area is x. It's b squared, but b is root x, and root x squared is just x. So we don't even really do anything to the area formula. Once we have our area formula in terms of x, that goes in the integral exactly as is. All you have to figure out with the integral then is, what are the bounds of integration? So now you can integrate this, and you get 81 halves. And we look for units. Did we get units here? No. All right, cool. We don't need to worry about units. Done. Yay! Ta-da! Oh yeah, it gets harder than this. But I think this is a nice introduction after, that wasn't like the full-on deep end, that was kind of like 5 feet deep. Now we're going into the kiddie pool. And it's gonna get harder. But if you can kind of see what's going on here, really the only way this gets more difficult is the shape, because then the formula for the area gets more complicated. And this region, what's b in terms of x? If you can figure out these two things, area formula and b in terms of x, then you're great. Because once you get those figured out, the actual integral you do is pretty easy.
No, why'd you say the isosceles triangle with base b as the first one?
Yeah, the first one.
Why is that one easier than the other?
Because if it's an isosceles triangle, the two legs are the same. And if the base is one of those legs, then one of the sides coming out of the plane is the same thing, and it's just 1/2 base times height is 1/2 base times base. So that's like the best situation. The worst situation is probably either the equilateral triangle or the other one, because those you then have to think a little bit more about what's going on. Sam?
I was gonna say,
The worst semicircles aren't bad. I'd probably say trapezoids, a star.
I think you should have a flat.
Yeah, a star.
I don't think stars would ever work.
I don't think a star would work unless you're ready for like. I mean-
But it would stick. It would make like negative, So, like it would go below. That would be like absolute value.
All right, so there's our star.
I don't know.
And if we draw a star and you want that to be our cross section, one of these edges would be the one having to come out or lie in the plane. And then no matter how you lay the star down, some of this is going into the page and some of it's coming out of the page, which is allowed, but we try to not do that.
Complicated.
And like, it doesn't have to be a semicircle. It could be a whole circle so that some of this cross section is coming out of the page at you and some of it is going into the page away from you.
So would you have that count as the area, the space that's not flat?
Well, the diameter would be the diameter would lie in and then you'd have half a circle on either side.
But you can just
But-
double the sound.
What's the area formula for a star anyway?
Triangle plus triangle.
I don't know. 5 triangles plus whatever this thing is in the middle. And what if it's a Star of David instead? That probably would actually be easier. So no, we're not doing stars. That's a Daniel Carvente level obnoxious question. What if we take this ellipse and rotate it so it's diagonal and then spin it out of the page?
Why would you want it?
Because he loves math. Those are the axes. He would do that.
What's he doing in college?
I think math or physics. I expect him to get his PhD in either math or physics someday, because that's the sort of stuff he was thinking about when he was a junior. He would come to me as like, "What do you think of this?" I was like, "That's cool. It is cool." All right, in B, same region. So I scrolled past it, but it's exactly the same region in part B. So we have the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. The line x equals 9.
Yeah, we are.
The curve y equals root x. But now our cross sections are semicircles. So again, we draw our representative rectangle. Again, we are going to be perpendicular to the x-axis. That didn't change. This distance from the top to the bottom is still b. But now we come over here and draw our two-dimensional cross-section, and what's that going to be? A semicircle. So we come over here, draw a semicircle, and the bottom of the semicircle is the base lying in the plane. So this is B. And now you got to be a little bit more careful with a semicircle. What's the area formula for a semicircle? 1/2 pi r squared. Now you got to think about this for a second. What is r in terms of b? Yeah, so the temptation is just to say, okay, plug b in for r and I'm good, 1/2 pi b squared. But no, the radius is half of that base. So we're going to have 1/2 pi times a half b squared. So now it's going to be 1/8
It was 1/8.
pi b squared, because 1/2 gets squared, and then that's multiplied by a half, so we have an 1/8 pi b squared. And then we need to come back to this b and say, well, b is really something in terms of x. So we come over here and say base b in terms of x is the distance from the top of the curve to the bottom of this region, and that distance is still root x. So you take this over here, and we have 1/8 pi, and then root x squared is just going to be x. Now, once you got your area formula in terms of x, you can go to your volume and say integral 0 to 9 of that thing, 1/8 pi x dx. Go ahead and take out the 1/8 pi, make your integration that much easier, and you're on your way. So we get,
Square B.
because we're taking, so we have b squared is then x. So what do we end up with for our volume?
A number.
81 pi over, is that 16?
Yeah.
81 pi 16ths. And then I check my answer key and make sure I'm not lying to you guys. You did it! All right, so that's what that is. So tomorrow we're going to continue working through this packet. Tonight you have homework from last night due tomorrow. It's in the textbook. There's one problem in that homework that's dealing with cross sections. The rest are still in washers and discs. Yeah, so the first 4 problems. So the homework is 23, 24, 31, 32, all disc and washer stuff. And then 71, that's a cross section problem. Yep.
And you set the other packets on Friday?
And I'll give you this packet. We will continue working in class on tomorrow, and then that'll be due Friday. Whatever we don't finish in class will be homework.
But I have it now.
Oh, you didn't get it?
You only give us one packet.
Yeah.
But I have it.
Oh, we're not even going to get to the other packet tomorrow. I'll give out the other packet on Friday.
So we'll do like.
Oh, I did.
So we'll be working in this packet tomorrow.
Okay.
Ms. Gardner,
Yes, ma'am.
is it Raymond?
It's not Raymond.